For today and the next two lectures, we're going to be studying Fourier series. I'd like to give, today will be an introduction explaining what they are and how you calculate them. But I thought before we do that, I ought to give at least a couple minutes oversight of why and where we're going with them and why they're coming into the course at this place at all. So the situation up to now is that we've been trying to solve equations of the form y double prime plus ay prime, constant coefficients, second order equations, and the f of t was the input. So we're considering inhomogeneous equations. This is the input. And so far, the response then is the solution equals the corresponding solution y of t, maybe with some given initial conditions to give a particular, pick out a special one, we call the response. The response to that particular input. And now, over the last few days, the inputs have been, however, extremely special. For input, the basic input has been exponential, or sines and cosines. And the trouble is, we learn how to solve those, but the point is to see those seem extremely special. Now, the point of Fourier series is to show you that they are not as special as they look. The reason is that, let's put it this way, that any reasonable f of t, which is periodic, it doesn't have to be even very reasonable. It can be somewhat discontinuous, although not terribly discontinuous, which is periodic with period, maybe not the minimal period, but some period, 2 pi. Of course, sine t and cosine t have the exact period 2 pi, but if I change the frequency to an integer frequency like sine 2t or sine 26t, 2 pi would still be a period, although it would not be the period. The period would be shorter. The point is, such a thing can always be represented as an infinite sum of sines and cosines. So it's going to look like this. There's a constant term you have to put out front. And then the rest, instead of writing, it's rather long to write unless you use summation notation, so I will. So it's a sum from n equal 1 to infinity, integer values of n, in other words, of a sine and a cosine. It's customary to put the cosine first, and with a frequency, the n indicates the frequency of the thing. And the Bn is sine nt. Now, why does that solve the problem of inputs, general inputs for periodic functions, at least if the period is 2 pi, or some multiple of 2, or some fraction of it? Well, you can think of it this way. I'll make a little table. Let's look at let's put over here the input, and here I'll put the response. Okay, suppose the input is the function sine nt. Well, there's going to be a certain, in other words, if you just solve the problem, you know how you put a sine nt here, you know how to get the answer, find a particular solution, in other words. In fact, you do it by converting this to a complex exponential, and then getting the, the rigmarole we've been going through. So let's call the response something. Let's call it y. I better index it by n because it, of course, is a response to this particular periodic function, so n of t. And if the input is cosine nt, that will have a response, yn. Now, I really can't call them both by the same name, so why don't we put a little s up here to indicate that that's the response to the sine, and here I'll put a little c to indicate it's the answer to the cosine. If you feed in cosine nt, what you get out is this function. Now what? Well, by the way, notice that if n is 0, that's going to take care of a constant term too. In other words, the reason there's a constant term out front is because that corresponds to cosine of 0t, which is 1. Now, suppose I input instead an cosine nt. All you do is multiply the answer by an. Same here. Multiply the input by bn. You multiply the response. That's because the equation's a linear equation. And now what am I going to do? I'm going to add them up. If I add them up for the different n's and take account also the n equals 0 corresponding to this first constant term, the sum of all these, according to my Fourier formula, is going to be f of t. What's the sum of this, the response, the corresponding responses? Well, that's going to be summation an yn ct plus bn yn, the response to the sine. That'll be the sum from 1 to infinity, and there'll be a constant, some sort of constant term here. Let's just call it C1. So in other words, if this input produces that response, and these are things which we can calculate, we're led by this formula, Fourier's formula, to the response to things which otherwise we would not have been able to calculate, namely any periodic function of period 2 pi will have as the procedure will be, you've got a periodic function of period 2 pi, find its Fourier series, and I'll show you how to do that today. Find its Fourier series, and then the response to that f of t, general f of t, will be this infinite series of functions where the y, these things are things you already know how to calculate. They're the responses to sines and cosines, and you just form the sum with those coefficients. Now, why does that work? It works by the superposition principle. So this is true. The reason I can do the adding and multiplying by constant, I'm using the superposition principle. If this input produces that response, then the sum of a bunch of inputs produces the sum of the corresponding responses. And why is that? Why can I use the superposition principle? Because the ODE is linear. It's okay since the ODE is linear. That's what makes all this work.